Much of the wreckage of the Boeing RB-29A Superfortress remains on the high moor where the aircraft was destroyed. Serial number 44-61999 is still represented by extensive debris on a moorland plateau near higher shelf stones. Known as overexposed, this aircraft presents a rigid problem in modern aviation archaeology. Situated at an elevation of 2,000 feet above sea level, the airframe is legally and physically bound to the earth. Investigators face a strict operational limit. They must establish a visual condition baseline for a deteriorating aluminum structure without conducting any intrusive sampling. The site is protected as the remains of a military aircraft under the Protection of Military Remains Act 1986, while the fragile moorland environment makes any intrusive work extremely difficult. Tampering with, moving, damaging, or unearthing material would require formal Ministry of Defense licensing and any relevant environmental permissions. The impact site lies near the summit of higher shelf stones on Bleaklow Moor in the Peak District, where elevation, exposure, and legal protection combine to fix the wreckage in place. The documented grid location and elevation parameters govern all modern interaction with the site. They arrive with a strict mandate to observe and record the physical limits of the debris. The guiding principle governing this location is the in situ heritage boundary. This framework shifts the surviving wreckage away from any ordinary salvage logic and toward a protected memorial landscape. A formal plaque was erected at the site in 1988 to mark the 40th anniversary of the crash, reinforcing the memorial character of the landscape without changing the statutory boundary already governing the wreckage. The legal restriction prohibits any modern removal or salvage of the surviving structure. Traditional recovery logic prioritizes the retrieval of critical components for controlled laboratory analysis. The heritage boundary entirely reverses that logic. The components must remain exactly where they settled on the peat bog. The investigators must treat the remaining wreckage as a protected system where no material is moved, lifted, or removed without lawful authority. Within this boundary, investigators document the exact placement of the Boeing RB-29A structural sections as they lie at the 2,000-foot elevation mark. Because mechanical extraction is illegal, the archaeological value of the site lies entirely in its untouched geometry. The legal parameters force investigators to rely exclusively on visual footprints and spatial coordinates. The boundary transforms the sprawling debris field into a permanent outdoor archive. Maintaining the integrity of this archive means strictly enforcing the no-touch policies across the entire high moor terrain. When investigators evaluate the overexposed site, they are executing a condition baseline operation. They map the coordinates of visible structure to track the footprint over time. The documentation must therefore be absolutely precise to compensate for the lack of physical sample collection. The high moorland plateau serves as a permanent open-air holding area for the Superfortress. Those boundaries define the modern survey problem, but they also leave a deeper historical question. How did a strategic reconnaissance aircraft find itself intersecting a high moorland plateau? On November 3, 1948, the margin between safe clearance and terrain impact collapsed during an instrument flight in low cloud. 13 personnel were on board for a routine operational transfer from Royal Air Force Scampton to Royal Air Force Burtonwood. The aircraft carried mail and a payroll for personnel at Burtonwood, reported in one recovery account as $7,400. The heavy cloud layer forced the crew into a complete instrument flight environment, leaving them to judge position by time, heading, and expected progress across the ground. This operational constraint triggered a fatal navigational sequence. Low cloud denied the crew any reliable visual check on their position. If the aircraft's actual progress over the ground was slower than expected, the crew would have been geographically short of the point they believed they had reached. Relying on their time calculations and believing they had successfully cleared the high ground of the Pennine Hills, the crew initiated their letdown before the aircraft had passed the moorland. That premature descent placed their flight path directly into the rising rock and peat of Bleaklow. At roughly 11 o'clock in the morning, the aircraft impacted the rising terrain. The available accounts support a controlled flight into terrain sequence in poor visibility, but they do not fix a precise minute-by-minute error boundary. The aircraft was totally destroyed upon striking the high plateau. This immediate geographical reality forced a rapid operational response under severe environmental limits. The Royal Air Force Mountain Rescue Team, based at Harper Hill, reached the remote site at roughly 16:30 that same afternoon. The immediate response faced intense procedural and physical limits. The high moor terrain consisted of deep peat bogs and eroded gullies. The combination of fading daylight, freezing conditions, and thick fog dictated exactly what the ground teams could achieve. The severe weather and the unstable boggy foundation of the moor blocked trucks, road building, and any heavy recovery machinery. The rescuers had to traverse the approach route on foot, carrying equipment by hand. Operating strictly under these physical limits, the initial responders executed a specific trade-off decision. On the afternoon of November 3rd, they confirmed the crash site and the absence of survivors, but the recovery of the crew had to wait until the following morning. In the early hours of November 4th, a recovery party climbed back onto the moor. They recovered the dead, personal effects, and the payroll bag, while the shattered, heavy structure of the aircraft remained on the site. However, the massive shattered airframe presented an immediate logistical problem. Total wreckage recovery across miles of trackless acidic bog was impractical under the response conditions of November 1948. They made the operational decision to leave the heavy structural sections on the moor once the crew, effects, and payroll had been secured. The logistical limit of the peat terrain halted structural extraction during the initial response window. That practical pivot left the heavy engineering in place and demanded a completely different approach to any future archaeological documentation. The distribution of torn airframe components sits a short distance northeast of the higher shelf stone's trig point, with the memorial stone recorded at roughly 200 meters from it. This fixed scatter geometry creates a unique operational limit for modern heritage monitors. The specific environmental parameters of the Peak District strongly restrict standard archaeological excavation techniques. The debris rests on fragile and unstable peat bog ground. This saturated wetland dictates a hard environmental limit that actively governs how investigators can interact with the site today. Peat bog ground stabilization presents a severe mechanical constraint because the surface cannot readily support the pressure of modern mechanized extraction equipment. Introducing heavy-tracked vehicles, lifting cranes, or load-bearing stabilization frames would risk penetrating the thin crust of the high moor. This intrusion could damage the surrounding terrain and alter the spatial orientation of the historical artifacts. Because physical ground shoring and heavy material transport would require exceptional justification, licensing, and environmental safeguards, investigators normally substitute recovery operations with non-intrusive visual documentation. To secure historical data under these terrain limits, archaeologists establish a careful visual condition mapping operation. Investigators may establish a localized control point near the main debris zone and use photography, coordinates, and measured surface observations to build a non-intrusive record of the surrounding moorland. The survey pattern must be designed to cover the visible spread of the shattered aircraft while limiting unnecessary movement across the peat. The field personnel must constantly monitor their own physical footprint during this process. Even the repetitive walking paths of a small survey team can quickly degrade the saturated peat crust. The gridding process, therefore, has to avoid redundant passes. Operating entirely within this bounded search geometry, the mapping effort focuses exclusively on what remains visible above the soil layer. The heritage monitors identify heavy wing sections, fragmented fuselage panels, and major mechanical assemblies across the wide footprint, using coordinate logging and high-resolution surface photography to tag the exposed structures in place. Rather than gathering the scattered wreckage into a centralized staging hangar, they catalog the exposed structural fragments exactly where they settled against the terrain. Every measurement is taken with specialized equipment designed to operate efficiently within the severe moisture and rapid temperature shifts of the high-altitude environment. Visual condition mapping requires constant operational trade-off decisions during the field survey. When an investigator encounters a partially buried wing section, they must log the visible upper surface while leaving the hidden substructure unexamined unless a licensed excavation has been approved. No earth is moved simply to expose obscured structural joints or manufacturer serial numbers. The methodology forces the archaeological team to accept a partial data set regarding the underside of the wreckage in exchange for preserving as much surviving spatial context as possible. This strict evidence discipline protects the remaining historical orientation despite decades of erosion, corrosion, visitor pressure, and small-scale displacement. This rigorous mapping procedure establishes a durable visual footprint baseline, locking photographs, coordinates, and repeat observations into a recoverable record of the exposed wreckage at a specific moment in time. The grid verifies the outer boundaries of the wreckage zone and secures the relative positioning of the scattered structures. By strictly adhering to the foundation constraints, the heritage team successfully frees the layout of the event. Once accurately mapped across the surface of the bog, the resulting debris distribution reveals the precise, violent geometry of the impact. The physical evidence remaining on the high moorland plateau presents an immediate forensic contradiction for the survey teams. While the surviving central structure provides strong proof of the final kinetic flight path, the forward command section is physically absent from that record, leaving the primary mechanical data beyond direct visual confirmation. By examining the alignment of the coherent body wreckage, the investigative teams can read the broad kinetic debris dispersal. A shallow controlled flight into rising ground generates a structural signature that differs from a steep vertical dive, rather than driving the airframe downward to create a deep, singular crater. The low forward impact forced the aircraft to break apart across the terrain surface. The wing center section structures and torn fuselage framing form a visible trail across the upper peat, establishing the broad axis of destruction without requiring physical manipulation of the debris. While the primary kinetic path is fully verified by these massive surviving wing and fuselage sections, the investigation quickly encounters a strict physical limit at the forward edge of the central debris field. The sheer physical trauma of the horizontal impact sequence ruptured the heavy aviation fuel tanks housed within the central wing structures, producing the immediate ignition that marked the forward edge of the surviving record. This intense, localized fire imposed a severe thermal overprint across the forward section of the aircraft. Extreme heat can destroy lightweight aluminum structures, distort instrumentation, and erase delicate evidence that might otherwise survive impact. The post-crash fire was intense enough to leave melted metal and a tangled central wreck. This destruction permanently obscures much of the original forensic condition of the forward crew compartment. The fire overprint sharply limits any mechanical configuration data that might have survived the initial kinetic shearing. Because the flight deck was eradicated, investigators cannot physically confirm the final position of the engine throttle quadrant, the final reading on the barometric altimeter, or the exact control column inputs applied by the crew in the final microsecond. Any localized mechanical data that existed on the forward instrument panels was completely and permanently erased by the thermal event. They meticulously document the exact boundary where the coherent aluminum structure transitions into the melted thermal zone. By mapping this burn transition line, the heritage monitors separate the macro-level trajectory data the site can still provide from the micro-level operational data it cannot. The survey process must therefore rely exclusively on the remaining coherent structure positioned immediately behind the localized burn zone. The surviving coherent evidence successfully defines the overall trajectory and confirms the massive horizontal shearing forces of the crash sequence. However, the central structure tells only part of the story. The highest energy components traveled much further. 4 Wright R-3350 duplex cyclone engines help define the heavy debris pattern of the overexposed wreckage zone. When an aircraft strikes a solid surface at high speed, heavy concentrated components can tear away from the more fragile surrounding structure. Because these dense mechanical assemblies retain significant kinetic energy, they may continue forward after the main fuselage structure collapses. By plotting the resting positions of the 4 engine blocks, heritage monitors can chart an important part of the crash energy pattern. The 4 engine units rest independent from the central wreckage cluster. Alongside these dense, heavy power plants, investigators also document the main landing gear assemblies lying detached across the moor. This detached evidence provides spatial data that the main body cannot supply. By measuring the approximate relationships between the detached landing gear assemblies and the 4 engines, the survey grid forms a practical monitoring perimeter. This perimeter helps define the area that requires heritage attention while stopping short of claiming a complete forensic polygon for the entire event. While the surface distribution of these heavy assemblies yields valuable mapping data, Their massive localized weight and the changing peat environment create a proof ceiling regarding the subsurface structural condition of the site. The high-altitude peat bog environment consists of saturated and extremely soft earth. Over decades of environmental exposure, some heavy components can become partly buried, while erosion and peat movement can also expose parts that were once hidden. The densest artifacts are therefore not simply sinking in one direction. They are caught in a changing ground surface that alternately buries and reveals them. This shifting surface blocks the survey teams from examining the underside of the engines or measuring the fully submerged portions of the landing gear. This limit prevents investigators from mapping the settlement depth of the heavy artifacts, including the concealed lower engine cylinders and the buried portions of the primary landing gear struts. The survey must proceed under the strict assumption that the buried aluminum and steel structures are effectively lost to visual forensic science. With the total debris field mapped, investigators must now secure the physical baseline against an invisible environmental threat. The primary risk constraint facing the overexposed site is a combination of corrosion, erosion, visitor pressure, and unauthorized removal. Repeat photography shows that the site has changed across the decades, and that corrosion on aluminum and magnesium alloy parts has become more pronounced. The high moorland environment generates a continuous severe weather cycle that subjects the exposed metal to moisture, temperature shifts, and abrasive wind. This constant exposure forces heritage teams to document a 1940s aircraft structure that is visibly losing material condition over time. Across the site, high moisture peat creates an aggressive corrosion environment for exposed aluminum and magnesium alloy structures. Where aircraft skin remains in constant contact with saturated peat and standing moisture, corrosion can strip strength and thickness from the lower surfaces touching the ground. Over decades of exposure, the reaction leaves some remaining metal brittle, compromised, and structurally exhausted. The areas of wreckage resting directly against the earth are likely to suffer greater material loss than surfaces exposed only to air and rain. Heritage managers observing this degradation face a hard conservation dilemma. The historical airframe is weathering into the Peak District terrain. In a museum context, conservation might involve lifting, cleaning, stabilizing, and storing selected artifacts in a controlled indoor environment. But at this site, active conservation would require intrusive intervention, formal Ministry of Defense licensing, landowner support, and any relevant environmental approvals. The wreckage is also treated as a memorial landscape. For routine management, the safer ethical position is to leave the remains undisturbed. Because heritage teams and responsible visitors must not halt the decay by moving or treating the debris themselves, repeat photographs and surface observations become the main record of ongoing material loss, without claiming an exact chemical decay rate unless a dedicated conservation study has measured it. This strategy forces investigators to accept a partial success outcome. Non-intrusive mapping can record the broad kinetic footprint, and repeat observation can track visible change over time. But physical preservation remains heavily constrained by legal, ethical, and environmental parameters. The Boeing RB-29A remains anchored on the moor where it fractured, its exposed aluminum slowly surrendering to weather, peat, corrosion, and human pressure.